But before that, you can see these are all the things that we are going to. Groups of 2 in all colleges, please facilitate. What I want the students to do, this is the exercise that Professor Vanamala and I designed together. But it is not. Because if you see what we are saying here, explain your thought process. Okay, that means you're actually thinking visually. Yeah, it's very easy to see what the shortest path is, but how do you get to it? So thought process is nothing but a solution, right? Or an algorithm. Path from V0 to V3. Everyone understands that? So there are 2 problems there, top one and the bottom one. So maybe 5 minutes for the first one and 5 or 10 minutes for the second one. So it's about a 10 to 15-minute exercise because you need to write down your thought process too. Groups of 2 or 3. Ready, set, go. Papers out, pencils out, start writing. You take 1, 2. Okay, and put your thought process. What is the thought process? Pass control.
Axis V11, V12, V13, V14. And the second stage we have V21, V22, V23. And third stage we have V3. So here we have to start from vertex V0 and our destination is V3. So starting from V0, we find out the shortest minimum weight to reach from V0 to remaining vertices at stage 1. V1, V1, V11, V12, V13, V14. And by observing from V0, we can choose the path from V0 to V12. That is because that is the minimum weight, that is 1. And so our first selection is from V0 to V12. And again from stage 1, again we have to observe the all possibilities for next stage 2 starts from V12. That is from V12 we have 2 possibilities with weights starting with 9 and second is 16. So in those 2, we choose the minimum weight, that is from V12 to V21, right? So that is we reached at the stage 2, the V21 vertex. After that, we have to find out the to reach the last node V3 with the weight from vertex V21. That is the weight only possibility is 13. So finally we reach the vertex V3. So the path is here we start from vertex V0 to V3 is V0 to V12 and V12 to V21 and V21 to V3, that is 90. So total weight, sum of weights are plus 9 plus 13. That is 23.
Above diagram, if you apply the same thought process to diagram 2 below, it would not lead you to an optimal solution. Do you agree? How many of you agree with the statement that I made? If you apply the same thought process, then that won't get you the shortest path in diagram 2. Do you agree or you do not agree? If you agree, you say agree in the chat. I'll be happy to. But first, you answer my question. The question is, in the first diagram, the reason I'm going slowly, this is a very important concept, guys, okay? This lays the foundation for this chapter. And then this chapter, we are going to spend several weeks. Today is only the beginning. This chapter is going to take a long time, okay? So, what is the first one that we said? The first one, the algorithm was, we start at V0. We look at outgoing edges. There's an edge with 5, there's an edge with 1, there's an edge with 3. And we pick the shortest edge in terms of weight. So we take 1. So from there we go to V1. Okay. Now from V1, again I apply the same algorithm. Take the shortest edge. I take 2. Go to V2. And then between 4 and 7, I choose 4, I go to V3. So my total distance is 1 plus 2 plus 4. That is 7. Okay. So that is my thought process. Look at all the outgoing edges, take the shortest weight. Got it? Okay. Now, if I apply the same thought process to the second diagram, let's see if it works. So what is the lowest weight in from V0, 1, the edge 1, right? So I go V, take 1, come to 1, 2. That is stage 1. Okay. Now from stage 1, I'm going to select the lowest weight. There is one edge which is 9. There is another edge which is 16. So I take the 9 one. Okay. So I go V12 to 9 to V21. I come to the stage 2. Okay. Stage 2, what is that symbol there? V2 comma 1. 2 represents the stage. 1 represents the first node. That's why you see V21, V22, V23. In stage 1, that's why you see V11, V12, V13, V14. So we did 1 plus 9. Okay. 1 plus 9 is 10. So now we are in, once we come to V21, then there is only one edge, right? From V21, there's only one edge, you take 13. So 10 plus 13, that is 23. Okay. So we did 1, 9, 13. That's 23. Correct? That was the thought process, right? In figure 1, we applied the same thought process. In figure 2, we got 23. But can we do better than that? As somebody put an answer here in stage 2, the same thought process, if I apply to this multi-stage thing, it won't work. So why did I show two contrasting pictures? Because the fundamental concept of greedy algorithm is it is always looking for shortcuts. It's always trying to optimize locally. We call it local optimization. So at V0, if you look at it, I'm only looking at the shortest path with respect to V0. Yeah. So somebody asked a question, sir, what does V2.1 denote? Stage 2, first node. Stage 2, first node. Stage 2, second node. Stage 3, third node. In that particular stage, think of it as columns, right? Column and row. Think of it as a matrix, right? So V21, V22, V23. Okay. So greedy says optimize locally. And at every stage, you optimize locally. That is the reason why at every stage, V0, V1, and V2 in diagram 1, even in diagram 2, if you take local optimization means taking the lowest weight. So we know that in the above case, the first diagram case, that worked perfectly. Whereas in the multi-stage case, it did not work. So if it did not work, then what is the remedy then? How can we fix that problem? These are the kind of things that we would be learning. Okay, go to the next slide. So what we are doing is we are trying to optimize, right? Shortest. So An optimization problem is one which you want to find not just a solution, but the best solution, right? That's why we call it optimization. Okay. And if you look at the second bullet, that's why we say this particular algorithm sometimes works well for optimization problems. Why do we sometimes? Because the exercise showed you in some context it works, and in some context. So, third bullet shows you that the way it works in phases is at every stage you take the best you can get right now, without even considering what the future consequences are. Okay. In other words, it's called choosing the local optimum. Okay. And hoping that if I optimize everything locally, globally also it gets optimized. That is what we are hoping. But hope doesn't work, you know. Hope is hopeless. Okay, go to the next slide. Here is another interesting example. Since I am in US, I'm used to dollars, right? That's why you see uh, everything in dollars and cents and all that. Okay. So what is the example here? You want to count some money, and you always want to get it counting the fewest possible bills and coins. Imagine if you, now that the demonetization happened in India, uh, you go exchange a 500 rupee note, the bank can give you 500s, or they can give you five. I don't know, is there a 1 rupee coin or 2 rupees now? I don't know, right? They're not optimizing. They want to give the fewest number of bills to you in exchange for 500 rupee note. Okay, so what is the fewest number of bills you are given? 5 of them. But the bank ran out of hundreds, then they can give you, let's say, 50s, then they have to give 10 of them, right? So what greedy algorithm says is you always take the largest possible bill or coin that does not overshoot the limit. So here is a great example, right? To get $6.39, I know I have a 5 denomination because after 5 is 10, right? So I take 5. I can take 1. That's the second bullet, right? And 39. The coins that I have are 5, 1, 5, 10, 25, and 50. Okay. So I have to take 25 because 50 exceeds $6.39. Then I'm left with 14. So then if I can take 10, then I'm left with 4. I can't take 5. Then I take 4 ones and coins. Okay. So for with respect to US currency, then what we have as of today, the greedy algorithm always gives the optimum solution. Is there anyone who does not understand this? If you do not understand it, put it in chat. If you understand it. Okay. See, here is a counter case. Remember how when we are proving, we can always prove certain things don't work by giving one example to show that it won't work. Okay. So here is an example where he talks about crowns. I think it's Danish currency, right? 1 krone, 7 krone, 10 krone coins. Okay. So we want to use a greedy algorithm to count 15 krones. So how would you get 15 krones? You said greedy algorithm says take the highest denomination. So we'll take 10. So that is the first sub bullet. Okay. Now, if you take 1 crore, right, after 10, you cannot take 7 because it shoots the 15 value. So then the next thing is available is 1. So you have to take 5 of them. So the total number of coins should be 6. However, If you look at the third bullet, what is a better solution? Instead of choosing simply the highest value, if I choose two 7 crore pieces and then 1 crore piece, then I only need 3 coins. Okay. So which is an optimal solution? The second one, right? Because you want to use the fewest number of coins. Okay. Let me pause here. Any questions, comments? You all understand? So again, repeating the same thing, saying that you are basically making a sequence of decisions. And then at every point when you make a decision, the decision is locally optimal. Okay. And the idea is in some cases, they do add up to a globally optimal solution. In the case of US currency, you have seen that it is optimal. Okay. But in the case of Krone that we showed you, it is not optimal. Okay. Important to note that only a few optimization problems can be solved by greedy method. So we have set the foundations by giving you different sets of examples, including the very first exercise to show you greedy methods are great. This is how they work, but in some cases they can give us an optimal solution, and in some other cases they will not give us optimal solution. Go to the next slide, please. Okay, somebody said not clear whether we have to give priority to 7 or 10. Okay, going back to that one, right? So, if you follow greedy method, you will not optimize the solution of 15 crowns, because greedy says you have to choose the highest denomination first. Keep on choosing highest denomination until it exceeds the value that we are looking for. That is rule number 1 in greedy. So you have to choose 10, because that's what greedy method tells you to do. But if you do it, you are going to end up with 6 coins. But if you modify your greedy in some way, then you get a better solution with 2 7 crore pieces. Okay, go to the next slide, please. You're done with this? Okay. So see, this is the problem that we did as an exercise. Usually what I typically do, I give you an exercise which is from the material that I'm going to cover, just to make you think to begin with in a class. So that way, once your brain is warmed up, then it's easy to follow the lecture. Okay, we know this. Go to the next slide. So here is the thing that we talked about, right? See, greedy method gives you 23 as the thing, whereas the optimal is 7 in a multi-stage. So greedy method does not work. That's what we proved here. Go to the next slide. So how do we come up? Remember, I said explain your thought process, right? How you come up. This is the thought process. This is the algorithm in terms of finding out the minimum. He is always keeping track of where he came from and what was the weight of that, right? So if you look at V0 to V3, you're taking a minimum of that equation that you see there. I'll let you convince yourself why you got 3157. Can you go to previous slide for 1 second? Where are you getting the 3, 1, 5, and 7 numbers? See that 3, 1, 5, and 7 are the edges from V0. So you're keeping track of the history, the weighted history. Okay. So then you do 3 plus 2, 1 plus 9, right? 3 plus 2, 5. 1 plus 9, 10, 5 plus 5, 10, 7 plus what, 10, 17. So you get 5. 5 is the 3 plus 2 is the right way to take. So that's the reason why you go from V0 to V11 and from V11 to V21. Okay. Now go back to the numbers. Now, keeping track of these things, when we do these things, it is called just dynamic programming. Okay. We have a complete chapter on dynamic programming. Okay. The word dynamic programming is a misnomer here. I'll give a 1-minute explanation of what that is. Then we'll move on. Okay. Here is the 1-minute explanation. Remember, we did the factorial, right? Example in one of the classes, like let's say factorial 5. Okay. You say 5 recursively you do, then you say factorial 4, factorial 3, factorial 2, factorial 1. So I'll show you an example later where when you're doing those things, you are calculating. When you did factorial 5, you're already calculating what is factorial 4, right? Now when you're calculating it, right, and then in the process of doing factorial 5, you're calculating factorial 4, factorial 3, factorial 2, factorial 1. Correct? You all agree? What dynamic programming says is whatever you calculate, you save it. So that way, you don't have to recalculate the same thing over and over again. Because if it's a recursive call, factorial 5 says you can compute factorial 4. But we have already computed factorial 4 once, so we'll simply take the value. That's what dynamic programming says. So you're saving time. You are always keeping track of the problems that you have, the sub-problem that you have already solved. So that way you don't have to solve the same sub-problem 10 times. Okay? That is the essence of dynamic programming. Move on. Okay. Now I didn't take my tea break today. Yeah? What is the time? Okay. I will not take a break. We'll continue. Okay. Now we come into a slightly different territory. Okay. Very important concept. The entire computer science algorithm rests on trees. Okay. Tree data structures. We have not seen the tree data structure yet. We have not even seen stacks and queues yet. But I'll introduce you to the concept of a tree here. Okay. What is a tree? Tree is a connected undirected graph with no cycles. That's what a tree is. Did you learn that concept in your data structures class, first class, second year, first semester class, right? It's a graph with no cycles. Of course, it's an undirected graph. Okay. Now, what is a spanning tree? Spanning tree of a graph is, first of all, it spans all the vertices of the graph. Okay. That is, it includes every vertex and it's a subgraph of G. That means every edge in the tree belongs to G. It's a subgraph of G, but not the other way around, right? So you are coming, you have a graph. Remember, a graph can have cycles, right? What is the difference between a graph and tree? A tree does not have cycles. A graph can have cycles. Okay, remember that. Hardwire it into your brain. Okay. A tree is a connected, undirected graph with no cycles, whereas a graph can have cycles. So when you are given a graph, most of the computer science problems are graph oriented. These algorithms require a tree. So how do you come up with a spanning tree? Because a spanning tree is nothing but it's a subgraph of the graph, okay? With the condition that every edge in the tree belongs to the graph. However, it will not have a cycle because it's a tree, okay? Now then once you know what a spanning tree is, what is the minimum spanning tree? A spanning tree with the smallest total weight. Remember, all edges have weights, right? The weights can be cost, distances, or if I'm drawing a graph of faculty members, I'm connected to other faculty members. Some edges say bigger headache value, some have less headache value, right? Could be anything. Faculty members, I apologize. I cracked a joke on you actually. Same thing at work, right? You love to interact with some people, headache value is 0. Yes, C. Prakash is giving mathematical definitions there. Very good. We'll do that. I'm actually going to put let me see. Is there an animation on this slide or just click a couple of returns and see? Yeah, yeah, so minimum spanning tree is the least cost subset of edges of a graph that connects all the nodes. The key things are all the edges, all the uh, all the nodes should be there. Okay, remember that. Otherwise, it's not a spanning tree. Okay, so how do we come up with that? There's an algorithm. Everything, remember, this is an algorithms class. How do we do that? It's one thing to know what it is, it's another thing to know how to do it, right? So start by picking any node. Okay, so you have nodes here list. You do pick any least cost edge from the node in the tree to a node not in the tree and add the edge and the new node to the tree. Okay, stop when all nodes have been added to the tree. Okay, so hit return. So okay, continue. There's some animation here, right? So what did it say? Start by picking any node and adding it to the tree. Okay. Then see how the animation is working, right? We are going from 1, 2, 3, 4, continue, 5, okay, 6. What are we doing? We are picking the least cost edge. Okay. That's what we are doing. Minimum spanning tree. If you think some other it should be in the spanning tree, continue. See, you are making sure because you're talking about a tree, you have to make sure whatever edge you are adding is not forming a cycle. Okay. If you have a cycle, you break the cycle and you remove the edge with the greatest cost because the goal is to have minimum cost, right? Okay. See, Prakash, what are you putting there? Let me see. We, the word anxiety, the edges, blah, 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 set for graph, you're all right. Those are all formal definitions. They're all great and good. Okay, typical mathematical definitions, right? But I'm interested in giving them the working knowledge first, not the formal definitions yet. But I will be posting a document, tutorial on graphs. You will have all these formal documents, formal definitions there. Okay. So what did we learn here? Just want to make sure. We said we have a graph. Okay. From the graph, the goal is to get to a tree. Okay. Tree does not have any cycles. Graphs have cycles, right? And the tree that we are interested in is a spanning tree. What is a spanning tree? Spanning tree means it should include all the nodes of the graph. Okay. All the nodes of the graph should be in the tree and it will not have cycles. That is spanning, meaning your tree is spanning all the nodes of the graph. Spanning tree, when you are building the tree, you're always taking the lowest cost edge. You can start from any node. From there, you start building all the nodes, okay, with the lowest cost for each edge. That's how you get minimum spanning tree. Now, before you hit the next slide, for a given graph, would there be one spanning tree or many spanning trees? If I give you a graph and ask you to do, great. See, Prakash is on a roll because they understand graph theory, I guess. I hope these answers are coming from students, but not the faculty member, right? PVP Siddhartha, many. You're right. You can have many, many spanning trees. Okay, go to the next slide. Okay. So I do not know if you have heard about this traveling salesman problem in intermediate or engineering math in first year. Okay. So a salesman must visit every city starting from city A. Okay. And the goal is to obviously minimize the cost, right? Cost meaning, let's say, distance in this case. Okay. So how does he do that? He uses a greedy algorithm. He goes to the next nearest city from wherever he is. Okay. So if he is at A, he goes to B. Okay, and from B, whatever is the shortest, D is the shortest. Now he has a problem, right? From D, how will he do that? Right? Hit return. Continue. See, B to D. Then what happens? See that? So that means he has to come back again. Okay. From D to B, and then go from there to C, C to E. Cost of 16. What is an actual least cost path from A, D? So instead of trying to be greedy, going the lowest cost, to take AD and then BCE at a cost of 14. Now, really, the traveling sales guys in India, not only in India, everywhere, right? I do not know if they think this deep. Okay. Can you imagine where all of these things are applied when you think of these things? You all use cell phones, right? Is there anyone in the class who does not have a cell phone? Is that a stupid question? Everyone has a cell phone these days, right? Believe it or not, for 2 years, when everyone was carrying cell phone here, I did not carry a cell phone. So I used to go meet all these professors, right, in universities and all that, and meeting. They say, "Pratap, what, you don't have a cell phone?" My answer is yes, I don't have a cell phone. How come? In what age you are living? I said, no, I want to keep my life very simple and happy. And they say, what do you mean by that? I said, the moment I carry a cell phone, I would get 1,000 text messages from my wife. Why do I want to have the headache of getting 1,000 text messages every day from my wife? That's why I didn't carry cell phone for 2 years. Siddhartha, I'm seeing you put something in private for me. A graph with n vertices has n raised to n minus 2 possible spanning trees. Yes, yes, yes. I agree with all of those things. We'll come to that. We'll come to those things. Okay. Okay, good. Continue. Comes to, if you look at the different parameters, right? I'll let you convince yourself how these things came about, right? Uh, the formula is given there, but these are basically, if you're looking at minimum spanning tree at the bottom, you can see that basically these are n log n algorithms. Okay. N log n is good. I went all the way to the bottom. So n log n algorithm, that's what it is. Uh, we will come back to more complex analysis of these things as we go along. Okay. Uh, go ahead. Next slide. Okay. Leave it like that. We have about 10 minutes, right? So I want you to draw a spanning tree for that. How about we stop after doing this exercise? We have 10 minutes, right? Let's see if we can do 2 more exercises. Okay, ready, set, go. What is the, we'll do a group exercise here. What is the spanning tree here? Can somebody quickly put it in the chat? You get the spanning tree, A, B, E, C, D. Okay, excellent. Okay, continue. See, multiple spanning trees, right? Somebody gave A, B, E, C, E, C, E, C, D, but somebody gave here in this place B, C, D. See, the answer given in the chat is 1. There are at least 2 more in this class, meaning in this particular chapter. And then you have 2 very famous algorithms. One is called the Kruskal's algorithm for finding a minimum cost spanning tree. And the other one is called Prim's algorithm for finding a minimum cost spanning tree. Okay. One relies on lowest cost edge. Okay. So one is edge oriented algorithm. The other one is a vertex oriented algorithm. Okay. So we'll be looking at these 2 things in depth. Go to the next slide. Okay. So what is Dijkstra's algorithm? By the way, reading a slide would not give you a good feel for Dijkstra's algorithm. I have to share, I do not know if I shared with you this story, right? He's an amazing guy, yeah? I almost feel like Dijkstra's brain is as cherished as Einstein, my favorite Einstein's brain. He came up with this algorithm sitting in a cafeteria, thinking about the algorithm in his head and coming up with a solution in 15 minutes. 15 minutes, the entire algorithm in his head. And it was a perfect algorithm, no mistakes. I don't know how he did that. Okay. But you can see here how he does that. Okay. You are starting with marking a given node as known, meaning path length is 0. Okay. Then the second bullet is important, right? You are setting the distance in each neighboring node equal to the cost of the out edge, meaning you are marking the edge. If the length, if the out edge cost is say 6, right? So you are keeping track of that. That is what the second bullet says. Okay? And you are basically repeating like that until all the nodes are known. That means what is he doing? He's basically calculating the distance or the shortest distance from one node to another one. It's called node pairs. Okay. So once you calculate those distances, then it becomes easy. The third bullet point in the set. Yeah. So for each node adjacent to the new node, you are examining the neighbors we already know the distances, right? To begin with, initially. So you have some complicated process like that to come up with the shortest path. I'm just giving you a high level overview. It's not easy to understand it like that. Well, actually, I'll make you work an example. Okay. We'll be doing some examples on Dijkstra shortest path algorithm in the class. One of the most famous algorithms in computer science. Continue, next slide. And we'll skip this slide for now because when we do the example, then we'll come back to complexity analysis. You'll appreciate it. But the bottom line is it's a very decent, efficient algorithm. Yeah, again, skip the slide. Again, skip the slide because we'll come back to analysis. Okay. Yeah. Go to the next one. Next one. As I said, we'll come back to the analysis of the algorithm later. Go to the next one. I wanted to do one more slide and then we can wrap it up. Go to the next one. Go to the next one. Okay, stop here. So remember I said we have Kruskal and we have Prim, right? So here is the two things side by side. Sorry, I had to do a snip tool to cut and paste it here. The text could be a little bit messy. Okay. So you have two competing algorithms. One focuses on vertices and the other one focuses on edges. Okay. Both are good algorithms. Both have, I think, n log n if I'm not mistaken. We'll see how those two algorithms work in the next class. Okay. And then we'll also see which one can be used. Uh, where do you use Prim algorithm and where do you use Kruskal's algorithm? So we'll take a look at those things. Okay. So with that, we'll stop the class. 4 minutes. We have only 4 minutes left. Any questions, comments?